Okay, welcome everyone to the first Egenis seminar of 24-25 in the year. Before I introduce our speaker today, Mauricio Suárez, I just wanted to make a couple of quick announcements since this is our first seminar of the year. The first thing I wanted to do is just say a big thank you, and we can have a round of applause for Yoshi. So let's have a round of applause. Who has taken over this year from Rose in organising the seminars and just done a brilliant job. And if you look at the list of talks that we've got coming up, starting today or through the term, it's fantastic. And there's a lot of work behind the scenes. We're really grateful to doing that. Also, there's Maria. And thank you to Maria as well. A round of applause for Maria for organising our new free call. You see from the announcements, the idea here is that we ask our distinguished visiting speakers, and Mauricio very kindly did this for this afternoon, to meet our early career students, MA, PhD students, and postdocs to talk to them about their research. And we had our first session this afternoon, which was great, and Maria's very kindly taken the lead in organising that. So do get in touch with Maria if you want to be added to the list. The last thing I just wanted to say before we start is we have some, coming out of the all members meeting that we had last year, we had a bit of discussion about how to, the format for the seminars and also the discussion session. I'll talk more about that in a moment, but the main thing to say is, new innovation for those of you who have been to these seminars before, we'll have a short break, 5 minutes, a comfort break, as I believe it's called, between Mauricio's talk and the Q&A. You already learned. It's just for this week because it's such a demanding speaker, and we just go now, just so that's partly so you can get to the bathroom, what have you, but also because just to give people time to think about their questions. And the other thing that I wanted to flag is that for the first 5 minutes or so of the question session, we'll have a period where early career researchers, so again, MA, PhD students and postdocs that want to ask questions get priority to do so, and then we'll just go into our ordinary question session. So I'll say a little bit more about that break. Thank you to Celso for putting together some of the guidelines out of the discussion last time, and also Angela Cassidy. They are all, I know you will spend your time checking the Egenis SharePoint site, but the guidelines that we put together for our seminars and events are there on the Egenis SharePoint. If you get time to have a look and you have some suggestions, then just email me and let me know. Okay, I think that's all I wanted to say on the announcements, unless I've got anything. So I'm just really delighted to be able to introduce Professor Mauricio Suárez from the Complutense University of Madrid to kick off the seminars for this year. I was saying earlier in the pre-talks, it's particularly nice for me to do this because way back when I did my master's at LSE, and Mauricio has a long-standing association with LSE, I can vividly remember reading some of Mauricio's work on representation in science and art, and he was really the first person to kind of pioneer that as an area which is now become a big topic in our field. And I can remember being very excited about this and deciding to do a PhD on this, and and hating you ever since. But the time that I spent doing this. I've imposed this on all of my master's students for the last 10 years. They all, just passing on who will get to read Mauricio's papers. So it's really lovely to have you here. Mauricio, for those of you who don't know, has worked, as I said, on philosophy of scientific representation, particularly his work on representation in science and art, but also lots of other areas, philosophy of probability, philosophy of causation, philosophy of physics, and he was telling us earlier, moving increasingly into what's often called integrated history and philosophy of science, and with frequent visits to the history and philosophy of science department in Cambridge. And I think, given what I said about my historical associations with Mauricio's work, this is going to be a brilliant topic for the presentation, because I think he's going to be telling us about his new book that came out this year, which, if I understand it correctly, and I'm keen to hear more, is a sort of continuation of that long project that began all those years ago with that work. So we're delighted to have you here. Yeah.
Thank you so much, Adam, for the introduction. Thank you, Exeter, for hosting me. I'm delighted to be back in England. I got in last evening, coming from sunny and warm Madrid. It was rainy and desperately cold here. I had fish and chips and mushy peas for dinner. I haven't stopped having tea and biscuits throughout the day today. I am so comforted and delighted to be back. It's really, really nice to be back here. So let me tell you a little bit about the accidental history of this seminar, which started off as an idea that I ran past Sabina Leonelli, who, as you know, is a very enthusiastic person. And she said, "Oh, you must come to Exeter and present your book." And so we arranged a date for me a few months ago for me to come and give this talk. But in the event, she couldn't be here for the date that we had prearranged. So we changed that date to another date, but then I couldn't be here because I had some health issues and I couldn't travel. And so finally, I've made it, but Sabina is not here. So, but I'm so delighted to have you all in my audience. And anyway, she knows everything about my book, because I've been bombarding her with all kinds of messages and emails and so on. So the book came out in January, and I have been expanding already on some of the themes in the book. What I want to do here is to just basically tell you what's in the book. But in the question and answer, you can ask me further. And there are some new developments that I'm not going to say much about in the presentation, but I'm quite happy to talk about in the question and answer period. So the first thing to say about this is that, as Adam was saying, this goes back a long way. This is not a recent interest of mine. The book itself has been 20 years, or was 20 years in the making. It took a long time, yes, I know. That's partly because I was busy with all kinds of things, amongst other things, raising a child. But also, there's a reason why this book took a long time to come to full fruition, and that's to do with the fact when I started working on scientific representation, it was a pretty small field. I mean, there were 3 people essentially working on the topic. One was Bas van Frassen, the other was Rick Hughes, and then I said, yeah, I'll come and work on that too. And I thought, great, I'm going to have a field for myself for a few years, I'm going to be able to work on this. But immediately after I started working on this, suddenly a lot of people decided to work on this topic. So it really exploded. So within about 10 years of me starting working on it, there was an encyclopedic amount of stuff out there. You couldn't possibly hope to write anything like a state-of-the-art book on this topic. So, although the book has been a project of mine for a very long time and has been contracted with the University of Chicago for a long time, they were incredibly patient, understanding, and I just have nothing but the best things to say about her executive chief editor, Karen May-Kangas Darwin. She is wonderful. Although it's been ongoing for a long time, I really only finally came up with a plan for the book that was really feasible around 2018. And that was just to write about my inferential conception of representation, not to try to cover the whole field. It's far too vast by now. Scientific representation is really one of those huge topics. So the book was actually written during those 4 years. Mainly in relation with some visits that I was carrying out at the time at the Institute in a Circle. There are a few institutions that were key along the way. First of all, as Adam mentioned, my involvement at the LSE, and the SUF project begins at the LSE at some point in the late 90s, but then there was this really important moment in which the models as mediators people coalesced around the LSE. A lot of literature has come out of that. That really was the starting point. Then there are some seminars with Arthur Fine and Martin Morrison that were really instrumental in getting my thoughts organized around this topic. And these three institutions played a very important role as I was sort of moving on. First of all, the LSE, then I was just in Harvard University, got to talk to Hilary Putnam quite a bit about some of the main philosophical aspects of the book. And finally, as I mentioned, I spent some time at the Institute of Inner Circle, and I really wrote the book while I was visiting there. This is the table of contents. And in the table of contents, you will notice that there are three parts to the book, very distinct parts to the book. The first part is concerning modeling and its practices, and I emphasize the plural. The second part is concerned with the philosophical notion of representation, or the notion of representation as philosophically conceived. We were talking about this before during the pre-talk talk. And the final part is concerned with the implications in two very disparate fields. I do something that is unusual in philosophy of science, which is to connect with debates in the philosophy of art. And as I was saying, this has been a long-standing interest of mine. Finally, I have a kind of full development of how these ideas interlink. That's chapter 8. I want to say a few things about it today. This is a kind of explosive material that I really like, and I'm still working on that. And finally, I make a number of claims about how adopting this new conception of scientific representation ought to make you change your mind about most debates in scientific epistemology regarding the realism-antirealism direction. The middle part is divided in 4 different chapters where I argue against a certain type of philosophical account of representation and in favor of what I generically call deflationary accounts of scientific representation, and I'm going to try to say a few things about how I use those terms very quickly here. You will notice the cover, which is extracted from one of the case studies, and I was so pleased that I could use it in the cover, and I'll say a few words about that case study as well, for those of you who don't know it, so you will gain a sense of why it is so prominently on the cover. Okay, so in the first chapter, I'm basically just going to run chapter by chapter because the book has a logical structure, and you really, if you get hold of it and you want to read it, you ought to try to read it in order, although there are some chapters that you can skip. It makes sense to sort of start with the beginning. So it's basically a manifesto for a pragmatist inferential conception of scientific representation. But what I say in the first chapter, I try to make very clear, this is not a project in the semantics of science or in the study of the discourse or the language of science. Hello. Hi. So I'm not really doing philosophy of language in this book at all, and I'm not really interested in developing an inferential semantics for scientific terms. That's not the project. It really is a project that looks into the modeling practices of sciences, of the scientists in their practical contexts, and tries to develop some materialistic philosophy of scientific modeling activity out of that, which is rather independent of any analysis of the language that scientists use to refer to those models, or more generally to describe their scientific work. And I want to say that, and I make a case for that in the first chapter of the book, because I want to distinguish this project from anything like this sort of inferential semantics that has been doing the rounds in the philosophy of language, coming from Brandon and others in the Pittsburgh circle. It's a completely different project, and in fact, you can adopt either an inferential semantics of the sort they develop, or a classical, straightforward referential semantics to understand what's going on in this book. It's pretty neutral with respect to this debate in the philosophy of language. The one thing that it is, and I was talking about this before in the pre-talk, the one thing that it is a critique of some established dichotomies in the field, in the philosophy of science. And in particular, I started off working on this as a way to try to mount a critique of Ian Hacking's distinction between representing and intervening in his very well-known book. I'm sure you're very much aware of that book and you know it very well. In that book, Hacking makes a contrast between, on the one hand, representation, which is a sort of relation between theories and the world. That's the first part of the book. And intervention, or intervening, which is the second part of the book, where he studies the material practices in laboratories and mounts an argument for a kind of scientific realism on the basis of that. And I've always had this feeling that this is a false, flawed dichotomy. So part of what is going on in the book is trying to argue that there is a lot of activity going on at the level of representation, that we shouldn't understand it as a sort of self-standing metaphysical relation, but it pays off to try to understand scientific representation in its context as an activity carried out by scientists too. And as I was saying earlier, I also think on the level of intervention, there's a lot of modeling and representation going on. So in the end, I think this is not really a true dichotomy. So in part, that's what's going on in the book too, and that comes to the fore in the final chapter on scientific epistemology. The second chapter is where I do history, and that's something that got me really excited, and I haven't been able to stop doing it since. That's partly the reason why I keep going back to Cambridge. So the second chapter tries to trace back what I call the modeling attitude, which is prevalent in scientific work nowadays, to its origins in 19th century science, mainly developments in both Britain and Germany. I distinguish something that I call the English-speaking school and the German-speaking school of modeling. And I locate a number of key movements and a few central concepts in the historical development of this modeling attitude. Let me just remind you that an attitude is a philosophical concept that has been extensively studied in recent philosophy of science, adopted by many contemporary philosophers. It's not a set of philosophical theses about science. It's rather a proposal of a particular stance, a particular way of doing science, perhaps a style of doing science. And in this case, the modeling attitude, which I defend, that was born in the 19th century or becomes dominant in the 19th century, is one that promotes model building as the central activity in scientific inquiry and the main or only source of worldly knowledge. There are other sorts of scientific attitudes, as well as philosophical attitudes one can have about science. And the one that I'm interested in this book is what I call the model. It's not actually invented in the 19th century. Galileo famously was doing modeling and presents us with models in his work, but it becomes dominant, I claim, in the 19th century, in the middle of the 19th century to the present day. So this is important not just for historical reasons, but because I claim that when you study the history of this modeling attitude, you can learn some philosophical lessons about the notion of representation that is proactive, that is operative in current scientific work. And particularly those lessons point towards a deflationary, not a substantive account of the notion of representation. So there are historical grounds for this sort of account of representation. The English-speaking school in that chapter is identified with these two characters that you all know, James Clerk Maxwell and Lord Kelvin. Both Scots, so there is a kind of tracing back of the modeling attitude to some of the commitments of the Scottish liberal educational system in the early part of the 19th century. And I managed in the book to pinpoint a number of philosophical commitments that come out of that then play themselves out throughout the development of this modeling attitude. So this is a dedication of my Scottish past, having been educated in Edinburgh, that had to come out at some point, and it comes out in this book, at the beginning of the book. There is something called the relativity of knowledge in Scottish common sense philosophy. It's basically nothing to do with the contemporary notion of relativism. In fact, it's not relativist at all from the contemporary point of view. It doesn't say that knowledge is relative to a system of values. What it says is that all knowledge of objects is relative to other objects. We only have comparative knowledge. And I'll run through a little example to try to illustrate that. This is related to Scottish abstract geometrical mathematics and what is called the method of exhaustions that comes from Simpson McLaurin, and puts analogy and analogical reasoning at the center of scientific inquiry. So the main example that these people use is in abstractive mathematics, how do you come up with the concept of a plane? And what you do is you conceive of a cube, a solid cube, and you divide it in your mind into perfect halves. Then you investigate the features of one of the surfaces, the intermediate surface. You find out that it cannot belong to either of the blocks, so it's therefore an abstract entity. And then you endow that kind of entity with a quality of its own. It's only relative to the comparison of the block as a divided entity, which you can only do in your mind in a model, essentially. So by drawing the analogy between the two situations, you come up with the notion of a surface plane. Now, what I claim in the book is that this is separable, others have made this claim too, that all this use of analogy and analogical reasoning in the early half of the 19th century in the Scottish common sense philosophy is completely distinguishable from the other commitment that all these scholars have, which is to the mechanical worldview. So it's well known that Maxwell and Thomson were very committed to the idea that the world is essentially understandable by mechanical means, and the famous ether was supposed to be a mechanical entity, endowed with mechanical properties and mechanical features, and ruled by mechanical laws. But this, I argue, is an incidental commitment. You can overcome the commitment to the mechanical worldview while remaining wedded to the relativity of knowledge and the centrality of analogical reasoning via models as the central way of doing science. And in fact, that I think is what had happened. We've left the mechanical ether behind, but we haven't left this distinctly Scottish modeling attitude behind. It has become the prominent way of doing science, not just in the physical sciences, but across a large number of domains. This is only in the second chapter, but then it goes on to discuss what I call the German-speaking school, which is very much centered around Helmholtz and Hertz and Boltzmann. They all participate in different ways in the development of this modeling attitude. Here, by means of something that has come to be known as the Bild theory, the theory of images, developed by Hertz, but pretty much rooted in Helmholtz's physiology of perception. And then finally, fully developed by Boltzmann into a full philosophy of science. And Boltzmann is famous for having published the article entitled Models in Encyclopedia Britannica in 1902, signal as a kind of paradigmatic article and put models centrally in the center stage of physics work at the beginning of the 20th century. So there's a continuation to this modeling attitude in what I call Helmholtzianism, which many people do, following Bachdal and other prominent historians. This is a methodology for doing physics by means of experimental interventions in systems, states, and potentials, as opposed to forces. Helmholtz is a very interesting figure. He begins neo-Kantian. He evolves into a kind of empiricist of a much more liberal sort. And the discovery of electromagnetic waves and the triumph of Maxwellian electromagnetic field theory plays a very prominent role in the development of Helmholtzianism. The characters in the German-speaking school and the English-speaking school are constantly talking to each other and writing to each other in all kinds of different languages. In German, in English, in French, they all speak and write in all those languages. And there's constant back and forth, for instance, between Helmholtz and Calvin. So the Bild theory is the modeling attitude of Maxwell and Thomson applied to mathematical representations of dynamical systems, states, and potential functions. So this is fully developed in the second chapter of the book. The critical aspect that comes out of this German-speaking school of modeling is the thesis of underdetermination, which is very explicit in Hertz and also in Boltzmann. So what comes out of this modeling attitude is the view that you can have different models of the same phenomenon. Those different models may have very different ontological commitments. And so, for instance, you can have representations of electromagnetic phenomena in terms of force theories, distance, forces are at a distance, or you can have it in terms of dynamical states. In the case of Helmholtz, they're completely incompatible, but they give a proper account of the phenomena in both cases. So there are a number of conditions that models must satisfy, but being fully in agreement with nature ontologically is not one of them. This is very clear in the case of Hertz, which imposes just this requirement of conformity. And Boltzmann adds this requirement of information transmission, and these are the only necessary criteria on builder, on these models of the world. So the modeling attitude brings with it a kind of very liberal outlook on how to do science, where you can have competing models being developed simultaneously of the same phenomenon, which are useful for different purposes and may have different pragmatic virtues. This is one of the results of adopting this modeling attitude, and I think the problem of underdetermination philosophically only becomes acute from the point of view of the modeling attitude, and once the modeling attitude becomes established way of doing science at the end of the 19th century, beginning of the 20th century. Now, this all comes from physics, but in the book I make some claims that it sort of spreads throughout, or in fact, it's not that it spreads from physics to other disciplines, but the modeling attitude is coming out of different disciplines at the same time. It's a sort of thing that is in the air, and it's happening in different places at the end of the 19th century, including biology, the development of biological models, and other fields, economics, very notably in the second half of the 19th century. So it's a kind of almost universal phenomenon affecting the way we do science in very many different disciplines at the same time. Well, then in the third chapter, I move on to discuss, I leave history behind, and I move on to discuss how models are used in practice. So the first thing that I do in the chapter is that I adopt and defend an old distinction between models that was presented by Max Black and has recently been defended by Axel Gelfart, which distinguishes models in four kinds: scale models, analog models, mathematical models, and theoretical models. There are many different classifications of models. People classify models depending on their interests in different ways, but this I find is a particularly congenial classification and division of the types of models that you find. So I adopted in the book. I would sort of give a brief defense of it, or mainly Axel Gelfart and adopted it. At the heart of some of these accounts, there's something called the interactive character of metaphors. So models are taken to be or to have some metaphorical character. And often it is understood in terms of the interactive account of metaphor that was provided by Black, by Richards. And I can say a little bit more about this and why it's an interesting philosophical thesis that is at the heart of this modeling attitude and the practice of these models. Perhaps we can talk a little bit about that in discussion, but basically the heart of this is that analogical reasoning does not depend on underlying pre-existing similarities between the two objects that are brought into an analogy, but rather the similarities themselves are created within the practice. So basically, when you come up with a model on this view, you're also coming up with a bunch of similarities between the model source and the target, which are not necessarily pre-existing the model. And that has consequences for how to understand the notion of representation that comes out of these models. Then I use three benchmark case studies for the study of analogical surrogate inferences in modeling practice. And this is what's going to explain the cover. One of the prominent cases is Benjamin Baker's Rail Bridge, or the one that connects Edinburgh with St Andrews. When you go from Edinburgh to St Andrews by train, you have to cross through this very remarkable bridge, late 19th century engineering building. And it has a beautiful history. It's recounted in part of the of the book. And one of the reasons why I want to deal with it is because I want my account of scientific representation and modeling to have a certain amount of generality. We were talking about this before, to cover different cases from different fields and disciplines, not just the pure sciences, but also engineering blueprints, plans, maps, architectural maps, graphs, and so on. The other reason why it is prominent and plays a role in the book is that this is the case study that was used by Michael Baxendale, the historian of art, in his influential book, Patterns of Intention. Many historians of art have dealt with this book, are very aware of what the book does. And I take a number of lessons from that book, which I then apply to the comparison between science and art in later chapters of the book. So it's important to me to use this as a case study. I mean, any historian of art will immediately associate the fourth rail bridge with Michael Baxendale's book and his thesis about interpreting art in that book. And then I used two other cases extracted from physics. I'm only going to talk a little bit about one of them. There are other case studies extracted from other fields, as I said, but I don't deal with them in so much detail. The first fourth bridge is important because of what I already said concerning Baxendale, but also because we have extensive chronicles of the blueprints that were produced around this bridge. And the claim here is that the context and the history are indispensable to understand how those blueprints represent the bridge, the parts of the bridge that they represent and what their intent is. The relevant similarities between the blueprints and the bridge can only really be understood if you understand the practice of modeling that underpins the construction of these blueprints. So there is, for instance, this famous living or anthropomorphic model. This is the one that made the cover, which is an example of model nesting. You see these three characters sitting here in different positions. They're exemplifying the cantilever principle, that is the principle according to which the bridge is constructed. So these two objects are anchored here, and these are the arms are in tension, and the levers are in compression. That's what holds the little man in the center upwards, and that's exactly the pattern of forces that operates in the bridge. This is a beautiful model exemplifying that principle. And as you can see, this living model, you can actually walk into it. People recreate it every so often. There's now a bunch of architecture students in Italy who are producing different versions of this model every 2 or 3 years, and you can literally see the videos how they put themselves in the different positions and so on. You have the representation, graphical representation of the bridge in the back. This is exemplifying that. And then you have, obviously, the bridge itself. So there's a nesting of models going on here. One model represents another, represents another. And I'm interested in this phenomenon of how models are nested structured. So often represent other models, which represent other models, which represent maybe models of data for the phenomenon of interest. So the inferences are operative go through all this nesting of models in all these cases. And this is a beautiful example of that. And moreover, it's an example of a living model or an anthropomorphic model that I was saying before, you can literally walk yourself in. The case of stellar astrophysics also has a long history to it. This is the Hertzsprung-Russell diagram that astrophysicists use to map stellar luminosity against the spectral class. And it was Eddington's great discovery, was that it's not just a statistical representation of different stars as observed on the surface of Earth, but it actually represents the life cycle of the stars. So stars will be born at some point around here, and throughout their history, they will move down the so-called main sequence. It is a dynamical representation of a dynamical process, namely the burning out of the fuel containing the inside of a star from its birth to its death. And what I do in the book is I look at the models that astrophysicists use to model the life cycle of stars and the assumptions, fictions or idealizations that go into it. I won't discuss them here, but they're mainly those 4 assumptions. So I'm going to put a long disquisition of the character of those assumptions, how they can be said to be fiction for idealizations. Nonetheless, they provide us with inferential shortcuts to the observational predictions that we want for every single one of the stars that you apply them to. So they have this predictive character, and the inferential rules that allow you to come to these predictions are very clear in the context of the model, even though the model is played with these fictional assumptions. I mean, we know that the stars have nothing like satisfying those 4 assumptions. Nonetheless, when you put them together in the context of a mathematical model, you get just the right predictions for the observable quantities of the stars. And I claim this is a general feature of models. Again, it links very nicely to the modeling attitude of Hertz and Boltzmann, where you can have fictional models giving you the right predictions that are just as acceptable as any other. The main thesis in this chapter is that models are representations in the sense that their representational functions are central to why they're models in the first place. What does this mean? It means that basically for me, in this book, model stands for representation. This is not to say that some scientific models can be used in non-representational ways. And there is this debate nowadays in contemporary philosophy of science raging over whether some models are non-representational. So I fall squarely on the side of those who defend that all models are representational, because they must have some central use that is of a representational kind. But then I have, as you will see, a very deflationary account of what that representational use is. It's actually quite easy to satisfy it. But at any rate, this is not to say that every use of a model is representational. Models may have many different uses, and some of them may not be representational. I mean, to just give you an example, you can have a helical structure made out of some concrete material, made out of wood, that represents DNA. It is a model of DNA in virtue of that representational use. That is, that we can use it to draw inference about DNA. But of course, you can use it for all kinds of different purposes. You can take the actual object and hit a nail in the wall with it. That's not a representational use of the model. There are all kinds of uses that you can give to models. But the claim in this chapter is that the reason why there are models in the first place is that there must be at least one central use of the model, in virtue of which we call it a model, which is the archetype for how the model gets used. So it is a contingent claim. It could be wrong. Maybe it is not true that all models are representational. But I claim, given a sufficiently deflationary account, you can make it fly. This claim does work. And there is some sort of inductive basis for making the claim. So part of the reason why I study different cases in the book, and I give a cursory account of different cases, it's because I'm aiming to have some quite enough inductive basis for this claim. So admittedly not very large number of cases, 3 benchmark cases plus another 3 or 4 cases that I look into, but from very different disciplines, different eras, different times, different uses in different fields and disciplines. So I'm aiming for diversity, a kind of diverse inductive basis to the claim that all models are essentially representations. That's the main claim philosophically in chapter 3. Then, well, chapter 4 really, what I do in chapter 4 is known to anybody who's looked into the literature on scientific representation. It just introduces 2 distinctions. I'll be very quick here. I distinguish representational sources and representational targets. That's very simple. A representational source is the model that's in the representational work. The representational target is whatever it is the model is. In the case of the DNA structure, the object sitting on your table is the source. The DNA molecule is the target. In the case of the rail bridge, the blueprints are the source. The bridge is the target. In the case of the astrophysics models of stellar formation, the mathematical models with all those 4 idealized fictional assumptions, the mathematics is the source, the target is the star, or rather the life cycle of the star, the dynamical phenomenon. And then I also distinguish between what I call means and constituent of representation. So means are basically whatever relations operate between targets and sources that allow scientists to carry out their analogical and surrogate reasoning from sources to targets. And there may be any, and there may be many different kinds, and they're contextually dependent. They change greatly depending on context. So you can have the same model source and apply it very differently in different contexts by means of very different relations. The means will differ. The constituent would be the universal relation in virtue of which the source is a representation of the target, if there is such a universal relation. Is there one type of relation that model sources and targets have, in virtue of which the model can be said to represent the target? This is a philosophical question, and philosophers have been asking this question for more than 2 decades now. My sense is that the consensus is moving to the answer that there's no such a thing as a universal relation between model targets and sources, in virtue of which the models are representations of their targets, but there are still irreducible defenders of what I call substantive accounts of representation that claim that there are. So it's still an ongoing debate. It was raging furiously 20 years ago, it's less so now. And this distinction attends to that debate. The constituent of representation will be the one universal relation and some kind of similarity that must obtain between targets and sources for the models to be said to be representations of their targets. My claim is there are no universal constituents, but there are many different means that operate in different contexts. Okay, so in the wake of this, there is this distinction between 2 types of theories of representation, which may be substantive or deflationary, and reductive or primitivist. Substantive accounts of representation argue that there is some constituent relation, that's the universal relation that obtains between targets and sources. Deflationary accounts, such as the one that I defend, and I'm not the only one by any means defending a deflationary account, are those that take it that there is no universal relation that constitutes representation, but there is a plurality of means that are relative in different contexts. And reductive and primitivist, the distinction there is those who claim that representation can be reduced to something else. If you are a defender of a substantive account of representation and similarity, for instance, you probably would want to claim that representation reduces to similarity, for instance. Primitivists are those who think that representation is a primitive notion that cannot reduce any further. Typically, substantivists would be reductive, deflationary would be primitivists, but it's not really an identification. It cuts across purposes. So there are ways in which you can defend a substantive primitivist account, and there are ways in which you can defend a deflationary reductive account. But typically, they go together. The 2 main theories of representation that are substantive and have been presented in the literature are the similarity and isomorphism theories. They've been defended by different authors in different versions. Basically, the similarity theory says representation is similarity. Wherever there is similarity, there is already representation. It's just a matter of observing, being attentive to it. Defenders of isomorphism claim representation is isomorphism. Isomorphism is a mathematical relation between structures, if you want to define it properly. So they have to really say something about how objects and phenomena in the natural world exemplify mathematical structure. Many defenders of isomorphism have a story about exemplification. And then once you know that objects or phenomena exemplify structures of a mathematical type, that you can claim that representation only obtains if there is isomorphism between those structures. This theory again has had its champions and defenders. I argue against both of them by defending this deflationary account, kind of deflationary primitivism of scientific representation that takes off from Rick Hughes' ideas. He produced this wonderful paper, 1997, Models and Representations. Many of us took heart from that paper. And he defended something called the denotation, demonstration, interpretation account, not strictly deflationary, but it can be turned into a deflationary, full deflationary account, and this is something that I do in this chapter in the book. I call that more sophisticated account that comes out of Hughes, the denotative function, demonstration, interpretive function account. There are reasons for all those terms. if you want any discussion, you can ask me about it. I can explain why I adopt all those. It's very verbose, I know what you end up with. But it's the best that you can do if you start off with the elements of Hughes' work. Basically, the idea that Hughes had is that the model denotes some phenomenon of interest, and there's some demonstration you carry out, the level of the model, and what you do is the final stage of that demonstration, you interpret it back in terms of the phenomena. And that allows you to draw some inferences via the model towards the phenomena about aspects of the phenomena that you didn't know before. So in that sense, the model can be said to be an informative representation of the phenomenon. And while I think there's a lot of good insight built into this account, I think that it needs to be developed further. Hence, there's something that I do in chapter 6 that I want to mention, because there's been a lot of discussion about the nature of scientific theory. And so one of the things that I do in that chapter is that I argue that the deflationary account of representation is neutral with respect to your account of scientific theory. I don't care what you think of theories. I can always flag in my account of representation. It's not going to depend on your views of scientific theory. Now, if you know something about the debate on scientific representation, this is a big claim to make, because a lot of people have actually defended the opposite, that your views on representation will depend on what you think the nature of scientific theory is. And so if you think that scientific theory is just a collection of axioms, the so-called syntactic view, supposedly defended by the logical positivists, a claim that needs a lot of study to be made properly. But if you claim that, then presumably you will want to say representation is some sort of linguistic relation of reference, some sort. While if you defend a semantic view of scientific theories, which recall is this view according to which theories are nothing but set of models, not linguistic entities, then presumably representation will not be a linguistic account or a linguistic relation, but it will be some sort of a structural or similarity account. Since theories are not bits of language, they cannot relate to their targets by means of linguistic reference. They must relate by other means. Now here there's a distinction to be made. There are those who defend the semantic view because they say theories are models and models are structures, and so therefore representation must be a structural relation, probably isomorphism. People have made this claim in succession. And it is a plausible claim to make in terms of the internal consistency of the view regarding scientific theories, but I don't think it works in practice. When you look at how those sciences represent, there's nothing like isomorphism doing the representing. There's an alternative, which I call the representational semantic view. Hughes was one of the earlier defenders. Also, Ron Geary defended this version of the semantic view. This view says theories are models, but it doesn't go on to say models are structures. It says that models are intended representations of their targets. Now, that view can be made to fly, I think, and it's perfectly consistent with a deflationary account of representation. And I showed it in this chapter in the book. And finally, there's another view that's been doing the rounds recently, which people call the pragmatic view of scientific theory, which is neither syntactic nor semantic. Actually, the syntactic view is not syntactic, the semantic view is not really semantic. The pragmatic view I argue in the book is not really pragmatic, because it continues to rely on mathematical entities. But anyway, that's a view according to which scientific theory is neither purely language, neither purely models, but it's a kind of hybrid bunch of activities grouped together. It's a kind of practice-based account of scientific theory. I don't know if it can be made sense of, but if it can be made sense of, it is compatible with a deflationary account. So that's my claim, conditional claim, right? So this is something else I do in chapter 6, and I thought you may be interested in it because I know philosophers of science debate intensely these views of the nature of theory. And well, it turns out nothing important hinges on that. Okay. In chapter 7, I looked at the view that I defend, which is the inferential conception of representation. And this is the conjunction of two minimal necessary conditions on scientific representation. The first one is that there is something called representational force, which I obviously have to explicate. that goes from the source to the target. It's a kind of asymmetric relation in practice, in the practice of modeling. And the other one is that there are specific inferential capacities suited to the target. That is, that the source must be suited inferentially to the target in order for it to count as a scientific representation of the target. I can unpack these two conditions, but let me tell you what I do in the book is that I connect them with thesis defended by Hertz and Boltzmann in the development of the modeling attitude in the 19th century. So I claim that they emerge naturally from the modeling attitude itself. I can say a lot more. I can say a lot more about this discussion. Let me just quickly go through the arguments that I put forward in this chapter in favor of this view. First, that it overcomes all the objections that make reductive, naturalist, or substantive accounts of representation impossible. That it overlaps nicely with this modeling attitude and its emergence historically in the 19th century. That it simplifies on Greg Hughes' inspired sophisticated version of his account, and that it accommodates all the case studies in the book, including the astrophysics case studies and others. So those are the arguments I basically put forward in favor of this view there, and we can, if you want, ask me again in questions, and I'll tell you more about them. The three case studies are reviewed in order to locate the following four elements, which are really essential to the account. The ostensible aim of model building activities, surrogate inference drawing in all cases. What you do when you build a model is to try to get or develop a tool that would serve you in inference to understand new aspects of the target system you didn't know before. And that's the ostensive aim of all model building in science that we've looked at. Much of model building concerns licensing. Licensing is establishing the norms for the rules of inference that operate between the model source and the target, but also within the model. What sort of dynamics cannot be operative in the model? How can you develop the model? How do you develop states of systems in the model? What sort of dynamics takes you from previous states of systems in the models to later states of systems in the model? And there is a sort of virtual dynamical equilibrium between these two necessary conditions. So you often adjust the representational force, the target of the model, and you refine it in line with the inferential capacities of your model. So if your model allows you to investigate and to deduce certain consequences of certain aspects of the target, you will turn that into the legitimate target of the model, and vice versa. Scientists often make adjustments of the other kind. So once they decide to develop a particular model of a particular phenomenon, they'll adjust the rules of inference in order to draw the right kinds of conclusions regarding the target system. And there's a constant dynamical aspect to model building that is accounted by attention between these two conditions. Then there's this upshot that if you think of modeling in this way, then modeling turns out to be something like the creation of communication channels that provide information about the target. But here it's very important to understand information in a non-veridical way, because models very often mislead about their targets, idealize them in all kinds of different ways, of course, fictionalize them in all kinds of different ways. So the information that a model transmits, it's quantifiable, mathematically quantifiable information, but it need not be veridical. So I adopt a non-veridical account of information in this part of the book. Okay, I want to move on to the philosophy of art. This excites me, and I will be very quick. I have 5 minutes to go, right?
Yeah, we'll have give us some questions. So.
Yes, and we have to have the break. So maybe I'll be so quick. Yes, maybe I'll be very quick about this. What I do in this chapter is I connect with the philosophy of art, and in particular, I connect with Bollheim's account of artistic representation as seen in. And this is a way of filling in this notion of representational force. So I used to employ Bollheim to fill in this notion of representational force. And so it involves this story, but the idea here is that representational force shares some of the elements of artistic representation according to Volheim, and in particular, the normativity, inflection, and artificiality aspects of seeing in. Seeing in is this phenomenon, according to Volheim, that we experience when we sit in front of a painting and suddenly begin to see what it is that we represent. It's not always immediate. For figurative painting, it's a very quick recognition. But for non-figurative painting, abstract painting, it can take a long time. And Volheim was known for these descriptions of him sitting in the museum, at the Tate Gallery, observing Rothko's paintings for hours until he finally got a grasp of what the Rothko painting represented, something pretty abstract. But they were representational paintings for him, and he saw them representing something.
We've got a coffee shop now for people in that position.
Yes, we have a coffee shop where we can go and do that. And then I used other paintings from classical history of painting to illustrate a number of pieces about this. This is Diego Velázquez, Pope Innocent X. It represents the Pope. No mystery about this. The Pope, as he was sitting in a particular room, waiting for Velázquez over a number of days. You probably know that Francis Bacon was really obsessed with this painting for years. He was really obsessed with the painting and came up with versions of it that look just like this. Now, here's the question. This painting is hankering after plastic features of the Velázquez. Bacon was obsessed with Velázquez and was obsessed with Velázquez's portrait of the Pope. Bacon didn't have a lot of interest in Pope Innocent X. It would be misleading to say that this is a representation of the Pope. This is a representation of the Velázquez portrait, which is a representation of the Pope. Now, if you're a believer in substantive accounts of representation, such as similarity or isomorphism, you're committed to representation being an equivalence relation, because of the logical features of similarity or isomorphism. So you must be committed to the conclusion that this is a representation of the Pope, which I invite you to think a little bit about and reject. That makes no sense of what Bacon was after when he was producing this painting. So from the philosophy of art, we can draw very immediately some quick lessons about the nature of representation, but I argue apply also to the philosophy of science. And this is one of the main arguments that has been put forward against substantive accounts of representation. You can rehearse it again in the context of the philosophy of art, and here it's not controversial at all. Every philosopher of art would be in agreement with the idea that representation is not in any way an equivalence relation, it's not reflexive, it's not symmetric, it's not transitive. So if they have no problem with that, why should, as philosophers of science, have any problem with it? Okay, I have one final slide on epistemology, but forget about it.